Section 7.4, Arc length and surfaces of revolution. To begin, we'll be looking at finding the arc length along a curve. Now, the way we do it is essentially break the curve into small segments and for each segment describe the distance formula on it. Now, obviously, if we let the number of segments become infinitely big, the size of each one becomes infinitely small, and therefore when you sum it up, you get that exact length. So in the same way we break area up into rectangles, we're just going to break up these curves into small little distance formulas, as you can see right here. So if we talk about any one little segment, its length is the distance formula, right? The difference in x, change in x, I should say, the difference between them, as well as the change in y, squared, added together, and square root. So this is going to be our main form just to talk about this piece right here. Well, what you can do is as you start putting them all together and you do a little bit of algebra and make it look a little nice, I'm going to skip those steps, you can essentially talk about L, when you want to start putting these all together, as the limit with the number of these segments becoming infinitely big, all right, as you add them all together. So as you can see, we're kind of creating a little Riemann sum here. So again, this is us adding up an infinite number of these little segments, and each of those segments, and this is the algebra I'm skipping, can be described as 1 plus the change in x over the change in y here squared times, on the outside of the radical, the change in x. So if you're interested in the algebra to go from here to here, it's just some common denominators, some multiplying, but this is the point. We can take the idea of any one of these little segments, and then as we put into our Riemann sum here and do some little algebra, we can make it look like this. Now, the really neat thing about this part of calculus is now that we're here, this part of it we can actually replace, as you can see, with the derivative. And the reason we know we can do that is because obviously we're going to be dealing with a nice continuous smooth curve here. And so when we talk about this rate of change, the slope, we know for a fact by the mean value theorem, there must be some value on this little interval whose derivative value is equal to its average rate of change. So we are comfortable and we have confidence by the mean value theorem replacing this kind of rate of change here, this with our derivative. And clearly when we talk about our change in x, that can be that little incremental delta x. So this formula right here and then adjusting it for y's are how we're going to calculate the arc length. Okay, it's really rooted in using and working with the distance formula, but by a little bit of algebra and our use of the mean value theorem, the formulas end up looking like this. Now, what's important to remember is with both of these situations, we're going to be finding the antiderivative of radicals, and that's not always very easy. So a lot of the work that we're going to be doing is talking about doing some algebra and other things to help us find our antiderivative of radicals, because right now we don't have a lot of tools to handle that. So we have to make sure whatever this expression here, 1 plus the derivative, right, under the radical works out to be, it's something that we can work with a radical and find the antiderivative. Okay, so up here I have the formula to remind us what we're doing, and we're going to be looking at the arc length of this curve from -1 to 1. So obviously we know where we're starting and ending, that's our a and b, and this is our function. Now what I like to do before I jump to the integral is just calculate the radicand, right? So the stuff underneath the radical. Let's just figure out what is 1 plus the derivative squared, and maybe do some algebra with it to the point where we feel comfortable placing it underneath a radical. So in this case, let's just begin by saying, okay, we're going to do 1 plus our derivative squared. So y prime squared. Okay, so that's going to equal 1 plus. Now the derivative here is obviously a chain rule. So it's going to be 1/2 times the quantity 1 minus x squared raised to the -1/2 times -2x. Okay, there's our chain rule, and we're going to square it. Now, if we simplify this a little bit, we can definitely get a 1 plus. Now, on the inside of this, remember the 1/2 and the -2, they just make -1. And this negative radical, right, this 1/2 power here, we can put in the bottom. So I can express all the stuff inside. This squared is basically negative. We still have an x. And the 1 minus x squared is in the bottom under a radical. So this is all the stuff here we're squaring. Now, once we get here, we can actually square that fraction. So this becomes 1 plus x squared over 1 minus x squared, because as you can see, it just takes care of each of those pieces. And then if we go ahead and find common denominators and simplify it and put it all together, it becomes +1 over 1 minus x squared. So the only step in here I kind of skipped was the common denominators, but of course the 1 here would just be 1 minus x squared over 1 minus x squared, so clearly the x squareds cancel, and you're just left with 1. Now, the reason this is okay is because this can be something that I would feel okay putting under a radical. Now, if you're looking at it right now thinking, I'm not sure that's going to be a good thing, just watch me do the antiderivative, and you'll slowly start to recognize why this sort of setup is actually something that's going to be okay. So to find our arc length, which we use, at least this textbook, like a lowercase s, is going to be the integral from -1 to 1. And of course, all we have to do is do the square root of, this stuff right here that we found. So we're going to take this 1 over 1 minus x squared, and of course, dx. Now, the reason this is really helpful, of course, is once I work out here, I can simplify it a little bit, and I mean, I can separately square root the top and the bottom. The square root of 1, that's just going to be 1, and the square root of the bottom is going to remain the square root of 1 minus x squared. Now, the reason this is so helpful, of course, and this does take a little practice to see this kind of in the future, this sort of, to me, when I put a radical on this, reminds me of this setup. So when I look at this, I can tell right away, I can definitely get the radical away from the bottom, and putting one in the, the top, and putting one in the bottom, this is just the inverse sign, right? This is arc sign. And that's an important thing with some of these more advanced integrals to recognize. So the antiderivative of 1 over the radical 1 minus x squared is the inverse of sine, arc sine. And of course, we're going to evaluate that from -1 to 1. So that means, using our fundamental theorem of calculus, we've got to do the arc sine of +1 minus the arc sine of -1. Well, the arc sine of 1 is asking at what angle, right, does the sine have a value of 1, because you're working backwards. So the angle for that would be positive pi over 2. And we'll minus. Now over here it's asking at what angle would sine's value be -1? Well, that would be negative pi over 2. So in this case, when you put all those together, the arc length along this works out to be exactly pi. Now, in our second example, we're going to do this along the y-axis. And as you'll notice, sometimes when we talk about values of y, we no longer use interval notation. You might see a little more inequality, and that's okay. Secondly, of course, we have an expression here, definitely in terms of x equals with y's. Okay, so just like before, let's calculate what 1 plus our derivative is squared, and hopefully, like I said, get that into a place where we feel more comfortable putting that under a radical. Now, this one's going to be a little more algebraic, but there's a pattern in this one to help us deal with a radical. So to begin, let's do our 1 plus our derivative squared. Okay, so in this case, it's x prime, if you will, because we have x equals. So the derivative is, and by the way, when I work with this one, it might help to go ahead and distribute this. So I'm going to view this as x equals 1/3 y raised to the 3/2 power minus y to the 1/2 power. Okay, so I'm going to basically take this stuff here and distribute it. It's going to help me do, as far as differentiate it, you just use power rule. So the derivative of the first one is going to be 1/2 y raised to the 1/2 power minus 1/2 y to the negative 1/2 power. Okay, now one thing that we're going to notice is when we start simplifying this, there's going to be a pattern. And this pattern is going to be something that is going to help us, again, when we place it under the radical. Now, this is very important to understand. The kind of problems we're going to have you do are ones where you can do some stuff algebraically to make it work out. There are many different integrals with radicals especially that aren't antidifferentiable. Like, you won't be able to work them out. We're not going to walk down that road right now. So to be clear, the kind of problems you're going to get are ones that when you put them under here, there will be things you can do to get the answer. Okay. Later on in the course, we'll talk about, what do we do with integrals when we cannot figure out what they are. Okay. And we'll also look at other strategies with radicals. But just to be clear right now, since we haven't gone too deep into, a more advanced integration, you're going to get things you can work out. So don't look at this and think they all work this way. We're purposely selecting problems that with what you have right now with skills, you'll be able to complete. Okay, so what we're going to do is we're going to go ahead and multiply this out because we want to see all the pieces, okay? And after we multiply this out, we're going to combine all the like terms, and then there's going to be a pattern that shows up. One that I think, again, is going to really make a big difference with the radical. So if I multiply this out, so, take this times itself, that's going to give me basically a 1 plus 1/4 y to the first minus 1/2 plus 1/4 y to the negative first. And again, you see these powers, of course, because you end up squaring these two. That's why we have first powers. And you multiply them together and double it, right, to get the middle term. And obviously, when you multiply them together, those opposite powers cancel out. That's why we just get the 1/2. Now, if we combine all of our like terms, what happens is we get a 1/4 y, and then we add in the 1 and the negative 1 have to give us a positive 1/2, and then we have a 1/4 y to the negative first. So here's what I want to focus on. We have a y to the first and a y to the negative first. Okay, that's one big clue this might work out. The reason for that is if this is going to be what we want, and what we want is a perfect square trinomial. We want something that factors to be a quantity squared. And that makes sense because if I can factor this to be a quantity squared, if I put it under the radical, it makes the radical go away. And then I can easily find the antiderivative. So what we're focusing on is this a perfect square trinomial? Well, the way you figure that out is you look at the first term, and you ask yourself, well, what are we squaring to make this? Well, what we squared to make this was 1/2 y to the 1/2 power, okay? When you took that times itself, we got the 1/4 y. This one, when we squared it, we were squaring 1/2 y to the negative 1/2 power. Now the check is this. Obviously, these are the things we were squaring that gave us our outside terms. What we want to check is if I multiply this times this and double it, do I get this, right? That's what makes a perfect square trinomial. So if you take 1/2 y to the 1/2 times 1/2 y to the negative 1/2 and double it, you end up with 1/2, okay? Because 1/2 times 1/2 is 1/4. Doubling 1/4 gives you the 1/2. There's no y, because when you take y to the 1/2 power and multiply times y to the negative 1/2 power, it just equals 1. So I know when I take this right here and this right here, the things we squared to make these outside pieces, when we multiply them together and double it, it does equal this. When you have that relationship, you do in fact have a perfect square trinomial. So that means that in here, when you factor it, you're going to have that 1/2 y to the 1/2, and then plus 1/2 y to the negative 1/2. I squeeze that in there. Okay, so again, the whole purpose of what this algebra was looking for this relationship. So we have a perfect square trinomial that factors to make this. This is something I absolutely want to put under a radical because clearly that squared is going to undo it. Okay, so now I'm ready to calculate my arc length. Now along the y's, right, we're going from 1 to 4 as far as y values. And again, it's going to be the square root of the 1 plus derivative squared, which again we found out to be 1/2 y raised to the 1/2 power plus 1/2 y raised to the negative 1/2 power. And that whole thing, of course, was being squared. So when I simplify that, obviously making the radical go away, all I'm left with then is the integral of, 1/2 y to the positive 1/2 power plus 1/2 y to the negative 1/2 power. And by power rule, I'm actually able to find that antiderivative. So this, right, is going to work out to be, 1/3 y to the 3/2. Remember, you have to add to the exponent first, plus y to the positive 1/2. And then, of course, we're going to evaluate that from 1 to 4. And when you work all that out, that works out to be a length of 10/3. Let's try one more example, this time again along the x-axis. Again, you can tell by using interval notation, but this is again going to give us an opportunity to practice identifying that perfect square trinomial. Again, something algebraically is going to be helpful so we can use, that squared factoring term to make the radical go away. Okay, so as always, let's start with 1 plus our derivative squared. Okay, so this will be 1 plus, and with this derivative, again by power rule, this is going to be 1/2 x squared minus 1/2 x to the negative second. Okay, now when we're doing that, obviously we're going to square it, and I hope right now you're already noticing what's going on. We already have the opposite powers, which we need. We are going to square it. But the thing is, because we still have this plus 1, we do have to multiply it out, combine the like terms, because we want to just have a quantity squared under here. So we do have to work it out. And just in case you're looking at this and seeing a similarity to where we're going to end up, we need to incorporate the plus 1, but it should work out. So if I go ahead and multiply it out, we have 1 plus our 1/4 x to the 4th, and then we're going to get a minus 1/2 when I multiply those together and square it. And then we're going to add on a 1/4 x to the negative 4th, because again, that's going to have the opposite power. So when I take my 1 and my negative 1/2 put together, we get basically that same setup. Here we have 1/4 x to the 4th. Now it's a positive 1/2. And then this is again going to be that 1/4 x to the negative 4th. This is very, very similar to that last one we just did a moment ago. So again, what we're going to do in our minds, right, is we're going to look at this, and our check is going to be, what did I square to make this? What did I square to make this? Well, again, looking back, This was 1/2 x squared. This was 1/2 x to the negative second. So the check becomes, if I multiply this times this and double it, do you end up with this? Well, 1/2 times 1/2 is 1/4. Doubling 1/4 is a half. And x squared times x to the negative second, that just equals 1. So again, it does fit. Okay, it works, which means we can take this whole thing and factor it, right, to 1/2 x to the second plus 1/2 x to the negative second squared. Now again, this isn't something that happens all the time, but obviously in order for us to do and practice finding arc length, we have to give you problems that have solutions, right? And to be honest, integrating radicals is not easy. So we're giving you things right here to come up with solutions to deal with the radical. Okay, so on this problem, finding our arc length, we're going to be integrating along the x-axis from 1/2 to 2. And again, under our radical, we're going to put in the 1 plus derivative squared, which we discovered to be 1/2 x squared plus 1/2 x raised to the negative second squared. All right, and of course it'll be dx because we're going along the x-axis. So when we simplify it, obviously our dreams come true and the radical goes away. So that means we can just do the power rule to go ahead and wrap this up. So its antiderivative here is going to be, as we evaluate this, 1/6 x to the third, okay, minus 1/2 x to the negative first, and then we're going to obviously plug in our 1/2 and 2 and work it out. So I'll cut to the chase. It works out to be 33/16. Now that we've talked about finding arc length, there's actually an application we can use now that we can calculate it to find the surface area of some shape that's being generated by revolving a line about an axis. So we've already done volume of these sort of shapes that are generated this way. This time we want to calculate the surface area of them. Now we already know how to calculate arc length. Okay, so if we break it down into one little segment that we were using the distance formula, of course, it obviously, if you rotate it around, creates what's called a frustum. Okay, this shape right here, kind of like a cone with its top cut off. Now, a frustum has definitely circular bases, top and bottom, one bigger, one smaller. So we have two different radii, because obviously we're looking at some sort of, line, little segment that we're revolving around. So while you may or may not know this, this is the formula for the surface area of a frustum. So this is the geometry we're using. We're going to imagine this shape, and this is the formula for its surface area. So the things we need basically are the arc length, which again, we just discovered how to find out. We already have a formula for that. Then we just have to multiply it by 2 times pi times this. Now this r is actually the average radius between the first and second. Now remember, this geometric formula we're going to combine and we're going to put it into a Riemann sum. So obviously this length kind of, comes down and shrinks down to an infinitesimally small amount, which means when you talk about the average of these radii here, that's obviously going to just become a number, okay? And again, by the intermediate value theorem, it's going to be some number between that, and same kind of situation with mean value theorem, we know it exists. So that's going to help us come up with this. So the geometry is going to look like this. We're going to need 2 pi. We're going to need the radius, which again is going to be basically a top minus bottom distance. Okay, I hope you see that coming. And then of course we're going to use the rest of the integral to be just that formula we use to calculate arc length. So basically we do the arc length of that little piece, and then using 2 pi r, we can figure out that distance around. And that formula for the surface area of a frustum, then as you sum it up in the integral, gives us the overall surface area. So when you put it all together, and again, as you can see, lots of little frustums put together on these weird little shapes. As you can see here, this is what the formula then looks like. So we have capital S. We're going to use that for surface area. We're going to go ahead and put the 2 pi out front, obviously, but we integrate here along the amount of the x-axis we care about. So this right here, this function, this is basically our top minus bottom. Okay, so this r of x is going to be that radius. So that's going to be the top minus bottom that we use when we want to calculate kind of where we're at. Because anytime, obviously, we're going along the x-axis, we want to know, okay, how far is it from here to here? Okay, so top minus bottom is going to do that for us. So when you're looking at whatever this function is, since we're probably going to be going around the x-axis, it's basically going to just be that function. Okay, so it ends up kind of being the same thing because it's usually going to be that function minus 0. And the rest of it, obviously here in the radical, clearly that's just our arc length, okay? And dx kind of goes with that. So we're going to kind of do the same setup. We're going to do the initial calculation of our radicand, and we're going to set up arc length. But the really nice thing about surface area is after we set up this integral here for arc length, we also get to put this top minus bottom expression on the outside. That's really helpful because, again, antidifferentiating radicals isn't easy. But having another function on the outside will oftentimes give us a way to substitute or give us some other algebra to do to deal with that radical. So it doesn't have to be just the radical. Having other stuff can make it easier. Okay, so again, here's our formula. We're going to be going around the x-axis. We're looking at the curve x cubed, and we're going to go from 0 to 1. Okay, so when we set this up, again, just looking ahead, I need to make sure I know a couple things, right? I want to know the radius. So again, that's going to be my top minus bottom. But because obviously when you think about the graph of this, x cubed over 0, 1, as far as the x-axis, the top is going to be the curve, the bottom is going to be 0. So when we talk about the radius, the top minus bottom is x cubed minus 0. So really, that just works out to be x cubed. Now, the other important thing is we got to calculate what is 1 plus the derivative, right, squared. Okay, because remember, that's the stuff as far as the arc length portion of it, I got to put on the radical. And because I like to work it out beforehand, making it as nice as I can as far as what goes under there, I like to work this out ahead of time. So in this case, we have 1 plus the derivative of 3x, so x to the third is just going to be 3x squared. And again, we have to square that. So it works out to be 1 plus 9x to the fourth. Now, unlike the previous problems, this isn't something that's going to, make the radical go away, but imagine having this on the outside. That's going to help us do a substitution. So when I calculate the surface area of obviously the solid generated by revolving this over this interval around the x-axis, it's going to look like 2 pi. Again, we're going from 0 to 1 along the x-axis. The radius is going to be the top minus bottom. So again, in this case, x cubed. Under the radical, for our arc length, we have 1 plus 9x to the fourth. And of course, we have dx. So again, the reason this is nice is while this doesn't make the radical go away, we can deal with it by letting this be our u value and just doing a basic substitution. So as always, we're going to say, well, our u is going to be that 1 plus 9x to the fourth, which means, of course, du equals 36x to the third dx. And since we're looking at only substituting in for x cubed dx, that means we're going to be throwing a 1/36 out front with our du to substitute in for the x cubed dx. So when you work this out, if I go ahead and put the 1/36 out front, remember we already have a 2 pi there, so what that does is give me basically a pi over 18, because obviously that's going to be cutting, it reduces the 2/32, right? So we have pi over 18. The integral is now going to go from 1 to 10. And again, the reason for that is the limits of integration here in x, when you plug them in here, convert to u values. If I'm doing a definite integral with substitution, I do prefer to change my limits of integration and just evaluate with the u values. Okay, so I took my 0 and 1, plugged them in here, and I updated those. So that means what's left, of course, is we have u under the radical du. And unlike maybe the previous problems, this is obviously just going to be a power rule level problem. So when you find the antiderivative of, u to the 1/2 by power rule, that's just going to work out to be 2/3 u raised to the 3/2. And then we can plug a 1 in and a 10 and get our answer. Now, if you want to work it out manually, it's not going to be a nice number. But when I use my calculator, I can approximate to be about 3.563. Okay, let's try one more example. This time, let's take the curve square root of 9 minus x squared and, over the interval -2, 2, revolving around the x-axis. And again, we're going to be looking at the surface area generated by doing that. Now, as always, I want to calculate my radius, and I want to calculate, the stuff under the radical. So in this case, again, my radius is going to be top minus bottom. Well, the top is going to be that 9 minus x squared. The bottom is the x-axis. So as always, that really just works out to be the function. So then I need to figure out what 1 plus the derivative, right, y prime is squared. Okay, so in this case, my derivative is again going to be a chain rule. So it's going to be 1/2 times the quantity, 9 minus x squared to the -1/2 times the derivative of the inside, -2x, and we're going to square that whole thing. Now this one's going to simplify very much like our earlier problem when we first looked at arc length. And on the inside of this is just going to work out to be the -x because the 1/2 and the -2 cancel. And then, of course, my 9 minus x squared, that's just going to be under the radical. Okay, so there's a square root there. And of course, we're going to square that. Now, once we simplify that out, that's going to be 1 plus x squared divided by 9 minus x squared. And just like we did before, finding common denominators gives us 9 divided by 9 minus x squared. Okay, so that means I'm going to have this radical on the outside and this under the radical over here on the inside here. And in this time, instead of doing some substitution, we're going to talk about how having multiple radicals can actually fix and help us do some other things. So I chose this example to show you some different algebra. So our arc length is going to be 2 pi. We're going to be going from -2 to 2. And then, again, our radius on the outside is the square root of 9 minus x squared. Under the radical for arc length, we have our 9 over 9 minus x squared, and then dx. Now, the reason this one works out so great is when you take a square root times a square root, you are allowed to multiply all those pieces together. So when we look at what happens when you do that, okay, we're still going to have our 2 pi out front, -2 to 2. But when you take this stuff in here and multiply it times this stuff in here under one big common radical, which is what, again, you're allowed to do, what you have to realize is that you have a 9x squared on top and a 9x squared on bottom and a 9 on top. So when you look at that, you have basically 9 times 9 minus x squared divided by 9 minus x squared. So as you can see, these are going to reduce. So you're really just left with here the square root of 9. So the reason this one is so nice is when you simplify it, you really come up with, as far as the thing in the radical, this whole piece in here is literally just going to turn out to be 3. Because you're just looking at the square root of 9. So that means you have 2 pi, and this antiderivative, of course, is simply 3x. You can plug your -2 and 2 in there, and this is going to work out to be a surface area of 24 pi.